In the coldest waters on Earth, evolution begins to warp. Creatures that should be tiny grow into giants. Spiders stretch wider than dogs. Jellyfish trail tentacles longer than whales. Even ordinary fish swell into oversized shadows. Why does the freezing ocean twist life into something so unnatural? Why do small species become huge while their warm water relatives stay miniature? And what hidden rule of nature lets this icy world build monsters that cannot exist anywhere else? Because beyond gigantism itself, there is an even stranger truth. These giants are fragile, born from stability so perfect that even a small change could erase them forever. Stay with me as we uncover why the Antarctic turns life into giants and why these giants may not survive much longer. If you were stranded in the Antarctic Ocean and made the mistake of looking down, you would expect empty blue water or clouds of drifting plankton. Instead, you would meet a realm where evolution has slipped out of control. Spiders with leg spans longer than dogs crawl across the seafloor. Jellyfish drift by with tentacles longer than whales. Even the most ordinary fish swell into unsettlingly massive versions of themselves. All of these creatures are real, shaped by an environmental force most people have never heard of. This is polar gigantism, a phenomenon that only takes hold in the coldest oceans on Earth. And at first glance, it makes no sense. In a place so starved of heat and food, you would expect animals to shrink to conserve energy. Yet here the opposite happens. Creatures grow bigger, heavier, and stranger. To understand why this frozen ocean creates giants, we need to look at the most dramatic example of them all, the colossal squid. Most people assume the colossal squid became enormous because of deep-sea gigantism, but that is only part of the story. These creatures live almost exclusively in the waters surrounding Antarctica, where temperatures hover around or even below zero. The seawater doesn't freeze thanks to its salinity, but the cold is still extreme, and the squids had to adapt in ways that reshaped their entire biology. Colossal squids are actually members of the glass squid family, named for their transparent bodies. Yet the colossal squid looks nothing like its delicate relatives. In the polar ocean, transparency offers little advantage, so evolution replaced it with thick insulation. The squid's reddish skin absorbs faint light from bioluminescent prey rather than reflecting it, allowing this giant to remain hidden even at massive size. With almost no predators except the occasional sperm whale, it evolved for stealthy ambush rather than escape. But why did it grow so large? The answer lies not in its prey, but in the water itself. Cold water contains far more oxygen than warm water, and oxygen is the fuel that makes large bodies possible. In warmer seas, there simply isn't enough oxygen to sustain enormous creatures, but at 0 degrees, that limit vanishes. Over millions of years, glass squids were pushed past their usual boundaries and transformed into giants. The colossal squid also combines two forces, polar gigantism and deep-sea gigantism. Living deeper than giant squids, they experience both effects at once, which is why they became the heaviest invertebrates on Earth, reaching more than 1,000 pounds. They are shorter than giant squids, but far bulkier, built like living fortresses of the deep. The colossal squid proves that cold water can turn ordinary species into giants, but it is far from the only case. Consider the sea spider. In warm coral reefs, these creatures are tiny, usually just 1 or 2 centimeters across, about the size of a house spider. They belong to the same family as their Antarctic relatives, yet the difference between them is almost unbelievable. In the Antarctic Ocean, that same spider becomes a 2-foot-wide monster. The rules that shaped the colossal squid reshape these spiders too. Cold water holds enormous amounts of oxygen, and sea spiders absorb oxygen directly through their legs. The longer the legs, the more oxygen they take in. In the polar deep, this system becomes supercharged, pushing them to grow far beyond their usual limits. But what do these giants do with their size? Unlike aggressive crabs or lobsters, sea spiders are quiet predators. They move across the seafloor on long, stilt-like legs, stepping over sponges and corals before using a needle-like proboscis to pierce a starfish and drink its insides. And because this is Antarctica, the starfish themselves have transformed into something equally unsettling. In the Antarctic, even familiar creatures become unrecognizable. Starfish that normally have 5 arms can sprout more than 50, turning into sprawling predators that barely resemble the delicate star shapes we know. These Antarctic starfish aren't just larger. Their entire biology has shifted. While typical warm-water starfish may live only around 5 years, Antarctic species can survive for more than 40. The cold slows their metabolism to a crawl, allowing them to grow slowly but steadily into towering, long-lived hunters. Their behavior becomes far more brutal as well. Like their tropical relatives, they pry open clams and digest the insides. But in this frozen ecosystem, they also prey upon each other. In these battles, the starfish with the most arms often wins, creating a strange evolutionary arms race powered by polar gigantism. The longer lifespan, the heavy body mass, the multiplication of limbs, all of it is driven by the same environmental forces. Cold water saturated with oxygen, and an ecosystem stable enough that slow-growing giants can thrive without being wiped out by rapid change. If you think giant squids and monstrous starfish are extreme, the Antarctic has an even stranger achievement. It has produced the longest animal on Earth, the lion's mane jellyfish. When fully extended, its tentacles stretch far beyond the length of a blue whale. The whale is heavier and more massive, but in sheer linear size, the jellyfish wins. And again, the reason traces back to cold water. Compare the lion's mane to a close warm water relative like the blue jellyfish. The difference is staggering. Blue jellies live in mild seas and never grow into giants because their environment doesn't force them to. The cold Antarctic, however, gives jellyfish access to enormous oxygen reserves while slowing their metabolism to a near drift. Over countless generations, that combination lets them grow tentacles of extraordinary length. This shows that polar gigantism is not a single species anomaly. It is a system-wide effect shaping every cold-blooded creature that depends on oxygen-rich water. From squids to spiders to plankton, the deep freeze pushes life toward extremes. So if cold water makes creatures bigger, why aren't polar bears or penguins examples of polar gigantism? The answer lies in how different animals use energy. Polar gigantism only affects cold-blooded creatures, the ones whose body temperature and oxygen intake depend entirely on the environment around them. For them, colder water means more oxygen, slower metabolism, and almost no energy wasted on producing heat. Their bodies become more efficient as they grow. Warm-blooded animals, on the other hand, face the opposite problem. They must constantly burn energy to stay warm. The larger they get, the more calories they need, and the polar regions simply cannot provide that much food. Still, these animals do grow bigger than their tropical relatives, but for a different reason called Bergmann's rule. Larger bodies lose heat more slowly. That is why polar bears are much larger than other bears, and emperor penguins dwarf most birds. Their size is a thermal strategy, not a path to becoming monstrous. They grow big enough to stay warm, but never so large that their energy demands become impossible to meet. Meanwhile, in the plankton world, even tiny creatures show the same cold-induced swelling. Antarctic copepods can be nearly 10 times heavier than tropical ones, reaching a full centimeter in length. For plankton, that is colossal, and it proves again that cold water reshapes life from the smallest scales to the largest. Even in a world defined by giants, not every creature follows the same evolutionary path. A few Antarctic species actually became smaller, not larger, through a rare process known as polar dwarfism. Some icefish and snailfish are noticeably smaller than their warm water relatives. Their extreme environment limits food for much of the year, so shrinking became a survival strategy. A smaller body allows these fish to mature faster, reproduce sooner, and endure long periods when food nearly disappears. While it is not as dramatic as turning into a monstrous giant, it is another way evolution adapts to scarcity. In a place where winters dominate the calendar and summers are brief, being small can be the difference between life and death. But the real twist is not just what evolves in the Antarctic, but how painfully slow evolution becomes here. In these waters, everything runs in slow motion. Chemical reactions, metabolism, and reproduction all decelerate. Some starfish take decades to complete a single generation. Sea spiders and urchins look almost identical to their ancestors from tens of millions of years ago. With almost no seasonal change, evolution has little reason to push species in new directions. The Antarctic becomes a vault of living fossils perfectly tuned to a world that barely changes. For millions of years, the Antarctic has been one of the most stable environments on Earth. The temperature barely shifts. The pressure stays constant. Predators are few. It is this extraordinary stability that allowed polar gigantism to flourish. When nothing changes, evolution can build slow, massive, oxygen-hungry creatures that would collapse anywhere else. But that same stability is now their greatest weakness. As the oceans warm even slightly, oxygen levels begin to fall. Metabolism speeds up. Those enormous bodies, once efficient and unstoppable, suddenly become liabilities. The very size that cold water encouraged becomes a trap. Sea spider populations already show signs of shrinking where water temperatures have risen. And for colossal squids, which depend on freezing oxygen-packed depths, a warming ocean could push them toward decline or disappearance. If you took any of these giants into a warm tropical sea, they would die. Not from predators, not from pressure, simply from the sunlight and the heat. They are creatures sculpted for a frozen world that is rapidly melting beneath them. And while they may look terrifying, none of them pose any real threat to us. No human has ever been attacked by a colossal squid. These are relics of an ancient Earth shaped by rules that are now unraveling. Polar gigantism shows us that when the world freezes, life does not fade. It grows colossal. But as that world changes, the giants who ruled it may be the first to fall. Across the Antarctic, evolution followed a path almost impossible anywhere else. Cold water filled with oxygen removed the limits that normally restrain life. Metabolism slowed to a crawl. Stability lasted for millions of years. In this rare combination of conditions, spiders stretched into giant jellyfish became the longest animals alive, and a fragile glass squid transformed into the heaviest invertebrate on the planet. But gigantism was never the goal. It was simply the shape life took when the deep froze and nothing ever changed. Now that stability is unraveling, warmer seas hold less oxygen, seasonal patterns are shifting, and the giants that once thrived in this frozen cradle are being pushed toward a world they cannot survive. Some may shrink. Others may disappear entirely. The colossal squid, the Antarctic sea spider, the towering jellyfish, all may become memories of an ecosystem that once allowed life to grow beyond imagination. Polar gigantism is one of evolution's strangest experiments, a reminder that when the planet changes, even the largest creatures can vanish quietly. But for now, these giants still glide beneath the Antarctic ice, living relics of a colder, older world.